Before we get to our more involved example of the propagation of random error, let's talk about the propagation of systematic error. And from an error treatment standpoint, the good news is that systematic error propagates differently and in a much more straightforward way than random error does. This is because systematic error has a consistent and known magnitude and direction. Through calibration and calibration studies, we can determine the direction of the systematic error, whether the instrument or the piece of lab equipment reads high or low, and we can test to determine how big that discrepancy is. So we know the value and we know the direction. And because systematic error is a property of the tool we're using, systematic error propagates additively because it propagates in the same direction and with the same value every time. One way you can think about this is if you were to deliver a solution over and over again with a pipette, and the pipette always delivered less than the desired volume by 0.05 milliliters, the systematic error associated with the use of the pipette could be written as negative 0.05 milliliters is the systematic error. Therefore, every time you use that pipette, if you haven't calibrated it, the volume you deliver is overestimated by 0.05 milliliters. And therefore, with each delivery, you deliver 0.05 mils less than you thought you did. And so after 3 deliveries, you've delivered 0.15 mils less than you thought you did, which is what we mean when we say systematic error propagates additively. We don't have to square the errors because we know their direction and their value. And so if we look at a problem like this, where we say we use a 25 mil volumetric pipette to deliver 100 mils, the phrase coming up, the pipette is uncalibrated with an error of plus or minus 0.03 mils. The pipette is uncalibrated is the key word in the problem that indicates we're dealing with systematic rather than random error. We want to know what is the absolute error in the final volume delivered. Knowing that this is not random error, we don't have to use a formula like the error is going to be the square of the first absolute error plus the square of the second absolute error, take the square root. We just need to know how many additions we've made and what the error in each addition is. Notice here we're not even necessarily provided the direction. We're just told that it is plus or minus 0.03 mils. So we're told the tolerance of the pipette, but not whether it's high or low by 0.03 mils. Nevertheless, if we know that the pipette is uncalibrated and the error is a systematic error, we can say that for the systematic error, the error is simply additive. If we do 4 additions with the pipette, each addition will be off by up to 0.03 mils each time, but it will always be in the same direction. So none of the individual errors cancel out. Instead, they add on top of each other. And the total error in the volume delivered is simply 4 times 0.03 mils. And the overall systematic error in using this uncalibrated pipette is plus or minus 0.12 milliliters. And so just recognize that systematic error propagates in a much more straightforward fashion than random error, because with systematic error, the errors are additive.